Air at 300 Kelvin, ordinary, room temperature air, squeezed through a narrow throat and blasted out the far end. Nothing is burning. Nothing is being refrigerated. So, how cold does it come out? Nothing is added to this gas, and nothing is taken away. The same air goes in that comes out. Yet it leaves thinner, far faster, and colder than any winter ever recorded on Earth. By the end you will predict exactly how cold, from a single number. 2 promises, and we have to keep both. Promise 1, adiabatic. The gas moves so fast that no heat has time to sneak in or leak out through the wall. In other words, whatever energy this parcel starts with is all the energy it will ever have. Promise 2, reversible. Smooth the whole way through, no friction on the wall, no shock in the middle, nothing wasteful inside. In other words, run the film backwards, and nothing you saw would look impossible. Keep both and the gas is isentropic. Entropy measures how disordered a gas is, how scrambled up its molecules are, and isentropic means that number never moves. Now hold on to this, because it is the trap at the end. Adiabatic on its own is not enough. Here is the whole video in one picture. 3 rungs, and that is the lot. We build them one at a time, then use them on a real nozzle. Now follow one parcel of air, this one, ringed in yellow, as it slides forward by a hair. In that hair's width, everything about it changes by a hair too: temperature, pressure, density. So read a little d out loud as a tiny nudge of. Here is the first law, written for that one tiny nudge. The change in the parcel's internal energy equals the heat you put in, minus the work it does on everything around it. That curly d just flags a quantity that depends on the path taken. In other words, energy in, minus energy spent, equals what is left inside. Promise 2 is what lets me write that work as PdV. Because the squeeze is smooth, the parcel always pushes with its own pressure, and the extra room it gains is dV. Pressure times the room it made is exactly the work it did. And promise 1 kills the heat term. Adiabatic means nothing crosses that wall, so delta Q is exactly 0, and a 0 term is a term you cross out. Watch the arrows die with the symbol. Now the only way this parcel's energy can change is by spending it on pushing. 2 facts, both earned in the perfect gas video. First, CV, the energy to warm 1 kilogram by 1 degree at fixed volume. So internal energy is temperature in disguise, a nudge of energy is CV times a nudge of temperature. Second, PV equals RT, R is air's gas constant, one fixed number. And careful with that little v, it is not the whole tank, it is the room 1 kilogram takes up, so V is 1 over the density. Rearranged, P is RT over V. Now the line holds only T and V. Look at the state of it, the T's and the V's are tangled on both sides, and while they are tangled we can do nothing. Separating variables means sorting the laundry, every T left, every V right. And here is why we bother, which nobody tells you. Once a side holds 1 letter only, that side can be totaled up on its own. That is what makes the integral possible. So divide both sides by CV times T. On the left, a CV on top and a CV underneath are the same number over itself, they cancel. On the right, AT on top and AT underneath cancel the same way. Sorted, T's left, V's right, 1 clump of constants between. That clump, R over CV, looks like more physics. It isn't, it is just a number, and we can earn it in 4 lines, right there. For that I need CVS twin, CP, the same idea, except now the gas is free to expand while it warms. And CP is always bigger. Always, because an expanding gas does 2 jobs with your energy instead of 1, warm itself up, and shove the surrounding air aside to make room. You pay for the warming and you pay for the pushing, and it turns out the pushing costs exactly R. That is the whole gap, CP minus CV is R. And that ratio, CP over CV, is what we call gamma, and it is always bigger than 1. Now for short lines. Gamma is CP over CV, so multiply by CV, CP is gamma times CV, put that in. Both terms on the left carry a CV, so factor it out. Divide by CV. The clump is just gamma minus 1. So swap the clump for gamma minus 1 and put it straight back into our main line. One nudge only moves a hair. To cross the whole nozzle we add up every single nudge along the path. That is all an integral is, a running total. Watch, 16 tiny nudges, added one at a time, make one whole change. So an integral sign goes on each side. The labels below and above say where the totaling starts and stops, on the left, from T1 to T2, on the right, from V1 to V2. Write those limits out in full, it is the notation people miscopy most. Gamma is fixed for a given gas, it does not change as the gas expands, so gamma minus 1 is no part of the totaling, and it slides straight out. And there is exactly one integral you need in this whole video, the running total of a nudge over itself is a logarithm. Now undo the logs. A logarithm and raising e to a power are opposite moves, they cancel, exactly the way squaring and square rooting cancel. So the logs simply vanish. 2 tidy-ups and rung 1 is ours. A minus sign in the exponent just turns the fraction upside down. And little v is 1 over density, so v1 over v2 is density 2 over density 1. That is rung 1, temperature against density. The pressure rung takes one line. P equals rho RT, density, times the gas constant, times temperature. Write that as a ratio between our two states and the RS cancel, so the pressure ratio is the density ratio times the temperature ratio. Now drop rung 1 in for that temperature ratio. Look at what we have, the density ratio, times the density ratio again. The same base twice. And multiplying two powers of the same base adds the exponents. The first has an invisible power of 1. 1 plus gamma minus 1 is gamma. Rung 2. Write it with little v instead of density, and there it is, the line this video is named after. P times v to the gamma is the same number at state 1 as at state 2, and those were any 2 points we liked. So it is the same everywhere in the flow. The temperature rung gives its twin for free. One rung left, and it is the one people skip. First the tool, because we use it 3 times from here. If x is y to the power n, then to get y back on its own you raise x to the power 1 over n. With numbers, 8 is 2 cubed, so 2 is 8 to the 1/3. A cube root undoes a cube. So take rung 1 and read it backwards. Density is stuck under a power of gamma minus 1, so raise both sides to 1 over gamma minus 1. On the right that is a power of a power, and those powers multiply. Gamma minus 1 times 1 over gamma minus 1 is 1. Density stands alone. Now feed that into rung 2, which wanted the density ratio. The powers multiply once more, gamma over gamma minus 1. That is rung 3, pressure straight against temperature. That's the ladder. 3 quantities, 3 rungs, no any one ratio and the other 2 come free. Now the warning that costs more marks than anything in this chapter. Every P and every T on it is absolute. Kelvin, not Celsius. Pascals, not gauge. And before we use any of it, I owe you one more thing. It's that badge. It has sat in the corner saying DS equals 0, and so far it has done no work at all. Let's cash it in. From the entropy video, the entropy change between two states is Cp times the log of the temperature ratio, minus R times the log of the pressure ratio. Isentropic means that change is 0. So set the left-hand side to 0, move the pressure term across, and divide by R. The log of the pressure ratio is Cp over R, times the log of the temperature ratio. And we already know Cp over R, Cp is gamma times Cv, R is Cv times gamma minus 1, so the CVS cancel, leaving gamma over gamma minus 1. Put it in, raise e to both sides, and out falls rung 3. The same line, from a completely different direction. When two roads meet, you can trust the map. Now let's meet gamma properly, the hero of this video, and so far I have only told you it is 1.4. Remember those two boxes? Gamma is the ratio of what they cost. The sealed one unit of energy. The one that is free to expand costs 40% more, and not because the air got hotter, it ends at exactly the same temperature. 40%. That is all gamma equals 1.4 is telling you. And why 40, and not some other number? Because of what air is made of. Air is nitrogen and oxygen, dumbbells, two atoms joined together, and a dumbbell can spin as well as fly. So count the places it can put energy. Flying in 3 directions. Spinning in 2 more. 5. Helium is one lone atom, so it has only the 3. And gamma is n plus 2, over n. 5 gives 7/5, which is 1.4, 3 gives 5/3. And remember R over CV is gamma minus 1? More storage makes CV bigger, so that shrinks, gamma slides towards 1. Our number is not a fudge factor, it is the shape of the molecule. So gamma is 1.4, and every exponent on that ladder is built from it. No magic, 3 ordinary divisions. Gamma minus 1 is 0.4. 1 over 0.4 is 2.5. 1.4 over 0.4 is 3.5. And 1 over 1.4 is 0.714. Back to the nozzle with real numbers. The chamber holds air at 20 atmospheres and 300 Kelvin. Our parcel set off from there and has been traveling ever since. There it is, where the pressure has fallen to 1 atmosphere. We want temperature, but rung 3 gives pressure in terms of temperature, the wrong way round. So use the tool, raise both sides to 1 over 3.5. On the right the powers multiply to 1, and the temperature ratio stands alone. 1 over 3.5 is 0.286, an exponent we earned. 0.05 raised to that power is 0.425. So the gas leaves at 42.5% of the chamber temperature. Times 300, 127.5 Kelvin. Minus 145 Celsius. But do not just take the number. Why did it get cold? Nothing cooled it. No refrigerator, no ice, nothing touching it. Go back to where we started, dE equals minus P dV. No heat came in, because we promised adiabatic. So the only account this parcel could draw on was its own internal energy, and it spent it, shoving the gas ahead of it out of the way. And internal energy is temperature. Spend the energy, lose the temperature. It got cold because it paid, out of its own pocket, for the room it made. One more, the same turn it over move, a third time. Raise rung 2 to the power 1 over gamma, and density stands alone. 1 over gamma is 0.714. 0.05 to the power 0.714 is 0.118. Turn it upside down, the gas leaving is 8.5 times thinner than the gas in the chamber. Same air, far more spread out. Watch. And now the trap I promised you. Put a shock wave in the nozzle. It is still adiabatic, no heat crosses the wall. But a shock is violent, and violence is never reversible, you cannot slam a shock. Promise 2 is broken, entropy jumps, and every rung of that ladder stops being true. Which is exactly where we go next. One gift before you go. Take this rushing gas and bring it smoothly to rest, no shock, no friction, and the pressure and temperature it settles at are the stagnation values. Nothing new, they come straight off this very same ladder.